Hello everyone, welcome to Probability and Statistics for Data Science. In this video, we're going to talk about the problem of estimating population parameters from data. Population parameters are quantities that describe a large population of interest. This could be, for example, the mean height of people in Spain, or the proportion of people in New York City that have a certain disease. Estimating such parameters is a fundamental problem in many different disciplines, including medicine, biology, politics, economics, and many others. In this video, we're going to introduce a very simple technique based on random sampling, which is extremely effective in practice. We're also going to provide a probabilistic analysis of this technique. Let's get to it. We're going to talk about random sampling, and we're also going to talk about the bias, which is a probabilistic evaluation of random sampling. Things will make more sense once we have defined random sampling. Then we will be able to define the bias a bit more formally. Okay, so our goal here is to estimate a population parameter. For example, we're in New York City. We want to do like an extermination campaign or something, and we need to find out what is the average weight of the rats in New York City. In principle, we could go out and catch every rat, weigh them, and compute the average. But of course, we're not going to be able to do that. Actually, if we did that, then the extermination campaign would be over, right? That is not going to be practical. So what do we do? Well, a pragmatic approach would be to just choose a subset of the rats, compute their average weight, and use that as an estimate. Essentially, that's random sampling, and it's incredibly effective in practice. So now we're going to define things a little bit more formally, and we're going to start analyzing this estimator. Not this estimator, this approach. Okay, so we want to estimate a population mean. We're going to take a look at a control scenario where we know the whole population. I'm going to use the height of 4,000 individuals as the true population that we want to, for which we want to compute the mean using a subset. So the heights I'm going to denote by h1 to hn. And what we really want to estimate is this average, which we could obtain by just taking each individual, measuring their height, taking the average of the whole population. This is too costly in general, so we're going to try to estimate this from a subset. Okay, I want to emphasize that this is an actual number. This is a constant. There is a fixed number that we want to estimate. Our goal is to approximate this number. In this scenario, I'm going to start by taking just 400 random people. And here what I'm showing you is that this is the histogram of the whole population in white. And what we're doing is we're just taking a few samples. So what our data look like, they look like that. And what we hope is that statistics computed on this subset of data that we're selecting at random, we just picked 400 people at random, are similar to the statistics that would be computed from the whole population. Realize that if we take 400 samples again, if we repeat our sampling process, we're going to actually get a different value of our estimate. So here in our original estimate, we have this approximation of the sample mean, which, as you can see, this is the sample mean of the 400 random samples that we took. It's actually very close to the population mean that we're trying to estimate. So this procedure of just taking 400 people, computing their mean, is actually very, very precise. But it has this wrinkle where if I repeat the process, I'm going to get a different estimate. So these are 400 other samples. As you can see, the estimate is different. It's still kind of close. It's still very close to the population mean, but it is different. Another 400 samples, another estimate. So when we discuss how good these estimates obtained from random samples are, we're going to have to reason probabilistically, because every time we measure, we obtain a different answer. In order to kind of capture this, I'm going to show you the distribution of the sample means of 10,000 subsets of size 400. So I repeat this experiment 10,000 times, where I pick 400 people and I compute their sample mean to try to approximate the population mean. And this is what I see. What I see is that all the histogram of these 10,000 sample means is actually centered at the true population mean, and what I see is that it concentrates very tightly around it. This gives me, this kind of guarantees that I am with very high probability, going to be very close to the population mean when I use the sample mean of this subset. Our goal is going to be to characterize the probabilistic behavior of such estimators. In order to do that, we have to actually define random sampling more mathematically, which we will do in a moment. Before, I want to introduce another. This is totally not because I forgot the order of my own slides. It is, right? I forgot that we were going to talk about population proportions before that, so you're going to have to forgive me for that. So before we go on to the mathematical formulation of random sampling, let's talk about another example where we want to apply random sampling, which is estimating a population proportion. So imagine that we're in the midst of the COVID-19 pandemic, and we want to estimate the prevalence in New York. In principle, we could go and test everyone and compute how many people have COVID-19 out of the total population of New York. But of course, that would have been impossible because there weren't enough tests in the middle of the pandemic, or at least at the beginning. So what do you do? Well, what you can do, before that, just to make it clear, there's this population proportion here, which is what we want to estimate, and it's a specific number, right? So it's 0.05 in this case. I just made this up, right? So 5% of the people in New York have COVID-19. Can we estimate that very accurately without having to go and do tests on the whole population? We're going to apply random sampling. We're going to pick a subset of people, test them, find out the proportion of people within that subset that have COVID-19, and call that our estimator of this population proportion. So what we're doing is there's a true, here, by the way, notice that this is logarithmic, because otherwise it would be we are only taking 1,000 random samples out of 8 million people. So otherwise I couldn't put the two histograms on top of each other. So this is the total population is 8.8 million. This is how many have COVID-19. And when we take random samples, this is how many we pick within a random sample that actually have COVID-19. And this is the ones that do not within the random sample. Okay, so hopefully that is clear. And now, as before, we get an estimate of the proportion. So in this case, out of the 1,000 random samples that we picked, 55 people had COVID-19. So that's our estimate of the sample proportion. It's close to the true proportion, but as before, every time we repeat this process, or if we were to repeat this process, we would get a different estimate. So these are 1,000 other samples. In this case, 49 people had COVID-19 out of our random sample of 1,000 people. In this case, 52 people had COVID-19. If I again take a look at what happens if I repeat this 10,000 times to try to get a feeling for the distribution of this estimator that we're building, then we see that, again, we're tightly clustered close to the true proportion that is 0.05, which is great news. So now we're going to try to understand why this happens. We want to characterize the probabilistic behavior of the sample proportion. Okay, so now we have reached to a point where we can define random sampling mathematically. The idea is that we have these fixed points, A1, A2, AN, which is this whole large population, and our data points are actually random. So this is very important to understand. The population is fixed. What is random is our sampling process, our measurement process. Every time we sample, we can interpret that as a random variable. And we're going to assume, and this is super important, these random variables are selected independently. It doesn't matter what I selected before. I'm going to just pick randomly from the population, no matter what my previous samples were. So in principle, I could pick someone twice, but that's going to happen with very low probability in large populations. Okay, so independently means that it doesn't matter who you have picked before. You just pick completely at random each time, and uniformly at random means that we have the same likelihood of picking anyone in the population each time we sample, which is very important because otherwise we're going to have subpopulations that could be important. And this happens, for example, when predicting presidential elections, which might not be sufficiently sampled. And that's actually one of the main challenges when you're trying to implement these things in practice, to make sure that you're sampling everything uniformly. Under these assumptions, these random variables that we have here are independent and they have the same distribution. I don't know why I repeated independent here twice. They have the same distribution. What is the same distribution? What is their distribution? Where the probability that they are equal to each of these values in the population is exactly 1 over n, because it's exactly the same. We have the same probability of picking any of the individuals in the population. Okay, so now we have a mathematical definition. We have n random variables that have this PMF and that are independent. So we can analyze the estimator obtained from those random variables. In particular, we're going to be interested to begin with in the sample mean, if we're trying to estimate the population mean. Now, before, in the course, when we're talking about the sample mean, it was just the arithmetic average of a data set. It was a deterministic quantity because the data set was deterministic. But now our data set is random because of this random procedure that we have to select the data. So the sample mean is a function of random variables. And therefore, it's a random variable itself, which we're going to denote by putting this squiggly line on top of it, which now means that it's a random variable that has a certain distribution. It has a PMF or a PDF. And in particular, we can analyze it, right? We can also apply the same idea to the sample proportion, in the case where we were trying to estimate the prevalence of COVID-19. Now our data here encode whether each person in the population has the disease or not. And what we're going to say is that the way we encode it is the corresponding data point is equal to 1 if that person has COVID-19. The random samples now are obtained in exactly the same way. We pick one of these guys independently at random and uniformly at random, so we have the same probability of picking each of them. And in that case, the sample proportion among the n measurements is just the sample mean, right? Because we obtain it by counting how many of the selected people had COVID-19 and divide by n. Okay, equivalently, we sum these random variables that we selected and we see how many. By summing, we're going to get the number of them that are equal to 1 and we divide by. Okay, so hopefully you see that there's this complete equivalence. The sample proportion is actually just a sample mean. Okay, so taking a step back, because we have introduced these random variables and that might be a little bit confusing, I have to emphasize that we're taking a frequentist perspective, in the sense that the parameter of interest, in this case the population mean or the population proportion in our examples, is deterministic. It's a fixed number. In the case of the population mean of the Heights, it was 175.5. It's a number. We don't know it, of course, but it's a deterministic number, and that's how we're modeling it. But the measurements are random. So when we look at our estimator, the estimator has a certain distribution that is going to have a certain relationship with the number that we're trying to estimate, in this case 175.6. And what we would like to show is that the distribution is kind of tightly concentrated on top of the parameter that we're trying to estimate. That's what we want. Okay, we want to this is what I meant before when I said that our goal was to characterize, or is to characterize, the probabilistic behavior of the estimator. In the remainder of this video, because if we did that completely in this video, it would take a couple of hours. In the remainder of the video, we're going to analyze the probabilistic behavior of the estimator in a very limited way. We're just going to ask, is the estimator centered at the parameter of interest? If I look at the distribution when I take a lot of sample means, is the distribution of the sample means centered at least at the true population mean? Let's see whether that's the case. This is called the bias of, before we see whether that's the case for the sample mean, let's first define the bias, which is the average error. We have these random measurements. We have a parameter of interest, which in our case is typically going to be the population mean or the population proportion. the bias of an estimator that is a function of the data and hence is random because the data are random, the bias is just going to be the mean of the error. Okay, so we take the estimator, we subtract the true population parameter, what's the mean of that? This essentially tells us whether the distribution of the estimators, when we repeat the sampling many times, is actually centered at the parameter of interest. If that is the case, then we say that the estimator is unbiased, which is something you must have heard because it's something that is said a lot in statistics, whether an estimator is unbiased or not. Okay, so let's remind ourselves, we have a population of fixed values. Every time we get a measurement, we sample one of those values, and hence we get these IID random variables, where for some reason I repeated independent here again, I copy-pasted, that have this PMF where the probability that each of the random variables is equal to an element in the population or an individual in the population is equal to 1 over n, where n is the size of the population. This is just a quick reminder of the mathematical definition of our measurements. Okay, so we're at a point where we can compute the mean of the sample mean. Okay, so the sample mean is random. When we're computing it from these measurements, we can see where its distribution is centered. So we plug in the definition. As usual, we apply linearity of expectation, and we see that it's just going to be equal to the average of the means of the individual random data points. So let's compute what the mean of each individual random data point is. The data points are selected among the population, so we have to sum their possible values. What are the possible values? Each of the individuals in the population, weighted by the corresponding probability. But the corresponding probability is just 1 over n because we're doing uniform sampling. So this is the average of all the elements in the population. This is equal to the population mean. This shows you that when you're doing uniform sampling, meaning you have the same probability of selecting all of them, on average, the average of the measurement that you obtain is the population mean, which makes a lot of sense. Now, by linearity of expectation, here we have the average, a sum of n population means divided by n. The mean of the sample mean is indeed the population mean. So this guarantees that this distribution of population means is going to be centered at the population mean. So the sample mean is unbiased. And this is why when we plot this numerically, we do see, that was a terrible arrow, we do see that this distribution of sample means, these 10,000 sample means, are centered at the population mean. It's not a coincidence. We prove that this has to be the case because we're doing independent and uniform. We're sampling uniformly at random and independently from the population. What about the sample proportion? Where we saw that the sample proportion at the end of the day is just a sample mean where we define the data points as being equal to 1 if a person has a certain condition, in our example having COVID-19, and 0 if they don't. So what we have to see is, so this is the sample mean. The sample mean is going to converge to the population mean. In this case, what is the population mean? Well, in this case, what is the population? Yeah, that's what I mean. This is the population mean, 1 over n times the sum of all of these guys. But when we sum all of those guys, what are we going to get? The number of people that have COVID-19, right? So it's the number of COVID-19 cases divided by n. This is the population proportion. Okay, so immediately from this result where the sample mean is centered at the population mean, we get that the sample proportion is centered at the population proportion because the population proportion is the population mean, or when we define the data as being equal to 1 if the person has the condition and 0 otherwise. Hopefully that was clear. Notice that we're assuming that when we sample, we can test people and we know whether they have COVID-19. So we're assuming that the tests are perfect. Otherwise, you would want to correct for that. And this is why when we look at this distribution of sample proportions, they are indeed centered around the true population proportion, which is 0.05 in our example. What about the sample variance? Well, we can do exactly the same thing. We have these data points. We take some random measurements uniformly at random independently replacement. The population mean is equal to this. The population variance, we can define it as each value centered by the population mean squared, and then we add. Okay, we sum over all the values. Now the question is whether the sample variance is unbiased. So it turns out that if you naively take your measurements, subtract the sample mean, and divide by n when you're doing the average, then you would not be unbiased. And this is exactly why we put an n-1 here. If you put the n-1 and you compute the mean of this random variable defined in this way, you're going to see that the mean is equal to the population variance. You might be wondering, why doesn't Carlos show the whole derivation as usual? Because this derivation is a little bit painful and it's not super insightful. However, I do recommend that you try to do it at home and you show that indeed, if you take, at the end of the day, it's just taking, applying linearity of expectation over and over and using our assumptions about the random measurements, these independence assumptions and the fact that they all have the same PMF. So I encourage you to do this at home, but it just gets very messy on a slide and it's not super insightful. But just so you know, that's why from the beginning we have defined the sample variance with this n-1 in the denominator. However, it's not super important because for large n, it's barely going to make a difference. Okay, so what have we learned? We have learned the definition of random sampling, and we have learned the definition of bias, which is, if you want, the average error that we're making. Where is this distribution of estimators centered when we compute them from random measurements? And we've seen that the sample mean, the sample proportion, and the sample variance are all unbiased. However, this is not the end of the story, because you might have noticed that I keep showing you these graphs where all the estimates are kind of very tightly concentrated around the true estimate, which makes us very happy. But in principle, this is also an unbiased estimator, right? If we had done this experiment and the histogram of estimates would be like this would also be an unbiased estimator because it's centered here, but you have a lot of instances where your estimator is extremely bad, right? Here we're making a mistake of half a meter in human height. That's basically useless very often, right? So we have to talk about under what conditions can we expect the distribution to be tightly concentrated around the population parameter. And in order to do that, we're going to have to discuss the standard error in the next video. Thank you very much.